Definition of infinite sets, Introduction. Previously, we spent some time looking at finite sets. Remember, a finite set is one where you can actually count all the elements. There's a beginning and an end to the counting process. It has a limited, countable number of items inside it. Now we're going to explore something quite different, infinite sets. These sets are fundamentally different from finite sets because they have an unlimited number of elements. Think of it as a set that never ends. No matter how many elements you count, you can always find another one. It might seem a bit abstract at first, but understanding infinite sets is incredibly important. It's not just a theoretical exercise. This concept is crucial for building a strong foundation in more advanced areas of mathematics, especially when you get into topics like calculus and mathematical analysis. These fields rely heavily on the idea of infinity, so getting comfortable with infinite sets now will really pay off later on. We'll start with the basic definition and then look at some examples to help you grasp the concept. So let's move on to a new and fascinating topic, infinite sets. Definition of infinite sets. What are infinite sets? So let's move on to formally defining what an infinite set is. As we discussed on the previous slide, we're now looking at sets that don't have a limited number of elements, unlike finite sets. Here, the slide states that an infinite set is simply a set that is not finite. What that really means is that if you tried to count all the elements in this set, you would never reach an end. You could keep counting forever, and you'd always be able to find another element. Think about it like this. With a finite set, like the first 5 natural numbers, you can start counting 1, 2, 3, 4, 5, and you stop at 5. With an infinite set, you start counting and you just don't stop. You can always add one more. Now, this next part is a bit more abstract, but it's a very important, precise way mathematicians define infinity. It says that a set is considered infinite if it can be put into a one-to-one correspondence with a proper subset of itself. Let's break that down. One-to-one correspondence means you can pair up every element in the set with exactly one element in another set, with nothing left over on either side. A proper subset is just a subset that isn't the whole set itself. It's missing at least one element. So imagine you have an infinite set, and you can take a smaller part of that set, a proper subset, and perfectly pair up every element in the big set with an element in the smaller set, and still have elements remaining in the original, larger set. That's a sign of infinity. For example, consider the set of even natural numbers. It's a proper subset of the natural numbers. You can pair 1 with 2, 2 with 4, 3 with 6, and so on. Every natural number has a corresponding even number, but you still have all the odd natural numbers left over. This demonstrates the one-to-one correspondence with a proper subset. Now, we're not going to get into the proof of why this definition works right now. That's a bit advanced. But it's important to understand that this isn't just a casual observation. It's a rigorous, mathematical way to define what we mean when we say a set is infinite. This will become important as we move forward, especially when we start looking at more complex mathematical concepts. On the next slides, we'll look at some concrete examples to help make this clearer. Definition of infinite sets. Examples of infinite sets. So far we've discussed what finite and infinite sets are, remembering that an infinite set just keeps going, and we can't count all its elements. Now, let's really nail down this idea with some examples. This slide starts with a really fundamental one. Let's look at the set of natural numbers. This is a classic example of an infinite set, and you'll encounter it a lot in mathematics. It's denoted by a special symbol. We write it as n, and it represents all the positive whole numbers. So it looks like this: 1, 2, 3, 4, 5, and then we have those 3 dots. Those 3 dots are crucial. They mean the list goes on forever. It doesn't stop at 5 or 50 or 5 million. You can always add 1 to the last number you've written down, and you'll get another natural number. Think about it. Is there a largest natural number? No, there is. No matter how big a number you think of, you can always add 1 to it. That's what makes this set infinite. Remember this example well, because it's the foundation for understanding more complex infinite sets we'll explore later, like the integers and real numbers. And understanding these examples will be important when we discuss concepts like one-to-one correspondence in the next slides. Now, let's break it down step by step to make it even clearer. We start with 1. Then, we add 1 to get 2. Add 1 to 2, and we get 3. And this process, adding 1, can continue forever, creating an endless sequence of natural numbers. This demonstrates perfectly that the set has no end, and therefore, it's infinite. Definition of infinite sets, examples of infinite sets, continued. Let's move on to our second example of an infinite set. As we discussed on the previous slides, remember that infinite sets are those where you can always find another element, no matter how much you count. Now let's look at the set of integers. We represent this set with a capital Z. That's Z as in zebra. The set of integers includes all whole numbers, and importantly, it goes beyond just the positive whole numbers we saw with the natural numbers. It includes positive whole numbers, negative whole numbers, and 0. So we can write it out like this: 3 dots, -3, -2, -1, 0, 1, 2, 3, and then more 3 dots. The 3 dots on both sides indicate that the set continues infinitely in both the positive and negative directions. Let's break this down step by step to really solidify the idea. First, consider the positive integers, 1, 2, 3, and so on. As we established with the natural numbers, this part alone is already infinite. Then, we add 0 to the mix. That doesn't change the fact that it's still infinite. Finally, we add the negative integers. -1, -2, -3, continuing infinitely in the negative direction. When you combine all of these, the positive integers, 0, and the negative integers, you get the set of integers, which is definitively an infinite set. Just like with the natural numbers, there's no largest or smallest integer. You can always add 1 or subtract 1 to get another integer. Keep this example in mind as we move forward, because understanding different types of infinite sets will become important later on, as we'll see on the following slides. Definition of infinite sets, examples of infinite sets, continued. Let's move on to our third example of an infinite set. As we've discussed with natural numbers and integers, identifying infinite sets can sometimes be straightforward, but this one requires a little more thought. This example focuses on the set of all real numbers between 0 and 1, and importantly, we're excluding 0 and 1 themselves. Now, you might initially think, well, between 0 and 1, isn't there just a limited number of fractions and decimals? And that's a very natural thought. But let's break it down. This set includes fractions like 1/2, 1/3, 2/5. It also includes decimals like 0.1, 0.25, 0.789. And it also includes irrational numbers. Remember those? Numbers like the square root of 2 divided by 2 or pi divided by 4. These are numbers that cannot be expressed as a simple fraction and have decimal representations that go on forever without repeating. It might seem like there's a limited number of numbers squeezed between 0 and 1, but that's where the concept of infinity comes in. There are, in fact, infinitely many numbers between 0 and 1. The key to understanding this is realizing that between any two real numbers, no matter how close together they are, you can always find another real number. This is a fundamental property of real numbers. Let's look at a step-by-step breakdown to illustrate this. Take the number 0.1. You can easily find another number between 0 and 0.1, like 0.11. But then you can find a number between 0.1 and 0.11, 0.111, and then 0.1111, and so on. You can continue adding ones after the decimal point infinitely, creating an endless sequence of numbers, all between 0 and 0.1. Similarly, if you consider 0.9, you can find 0.91, then 0.901, then 0.9001, and again, this process can continue infinitely. And remember, this isn't just limited to decimals. There are also infinitely many irrational numbers nestled between any two rational numbers, with their non-repeating, non-terminating decimal representations filling in all the gaps. So, while it might not be immediately obvious, the set of real numbers between 0 and 1 is definitively an infinite set. This is a crucial example to understand, as it demonstrates that infinity isn't just about counting whole numbers. It exists within the continuous spectrum of real numbers as well. In our next slide, we'll summarize the key takeaways from these examples and discuss some common pitfalls to avoid when thinking about infinite sets. Definition of infinite sets, key takeaways. Let's recap what we've learned about infinite sets with these key takeaways. First, and most importantly, an infinite set is simply a set that contains an unlimited number of elements. Remember, we previously discussed finite sets where we could count all the elements. With infinite sets, that's impossible. Secondly, because of this unlimited nature, you cannot count the elements of an infinite set and arrive at a final, definite number. No matter how long you count, you'll always be able to find another element to add. Think back to the examples we just explored. We looked at several examples of infinite sets. We started with the set of natural numbers, which we denoted as n. That's pronounced n, and it represents all the positive whole numbers starting from 1, 1, 2, 3, and so on, continuing forever. Then we moved on to the set of integers, denoted as z, pronounced z, which includes all whole numbers, a positive, negative, and 0. And finally, we considered the set of real numbers between 0 and 1, which, even though it seems confined to a small range, also contains an infinite number of values. Now, why are infinite sets important? Well, they are fundamental to many areas of mathematics, especially when you start studying more advanced topics like calculus and analysis. These concepts build directly on the foundation of understanding what infinite sets are and how they behave. In our next section, we'll briefly touch upon some common pitfalls students encounter when first grappling with the idea of infinity, so pay close attention to those to avoid making the same mistakes. Definition of infinite sets, common mistakes. Now we've been talking about sets that go on forever, like the natural numbers, 1, 2, 3, and so on, endlessly. It's easy to fall into the trap of thinking there's some ultimate number that is infinity, but that's not correct. Infinity isn't a number you can perform calculations with like you would with, say, 5 or 100. Instead, infinity is a concept. It represents the idea of something that continues without any bound or limit. It describes a process that never ends, rather than a specific quantity. This one is particularly tricky. It seems logical to think that if two sets both have an infinite number of elements, they must be the same size. However, that's not necessarily true. Believe it or not, some infinite sets are actually larger than others. For example, the set of real numbers is, in a very precise mathematical sense, larger than the set of natural numbers. This is a more advanced topic explored in something called set theory, and we won't be diving into the details right now, but it's good to be aware that infinity isn't just one size fits all. And that's perfectly normal. It's incredibly challenging for our brains to truly grasp something that has no end. We're used to dealing with finite quantities in our everyday lives. So, instead of trying to see infinity, focus on the defining property we've discussed, the ability to always add another element. If you can always find one more element, no matter how many you've already counted, then you're dealing with an infinite set. Let's move on to the final slide, which highlights some common mistakes students often make when first learning about infinite sets. This is really important because recognizing these pitfalls will help solidify your understanding. So, to recap, remember that infinity is a concept, not a number. Infinite sets can have different sizes, and the key to understanding infinity is recognizing the endless possibility of adding more elements. This concludes our introduction to infinite sets. Hopefully, you now have a solid foundation for further exploration in more advanced mathematical topics like calculus and analysis.